ready to... So good morning, everybody. I got 11:10 now. We've got 313 of you here, so welcome. It's great to see you. It's a sunny day in Toronto, and we might as well just get going. Let me put on my screen share here. Get my ducks in a row. Hope everybody's doing well, and I hope everybody got some sleep last night. Woke up a bit early, and then I had I went for a jog. Actually, just wanted to get some energy out. So like, it must have been 5:45. Went through a jog through High Park and looked out over Grenadier Pond and saw some ducks, and that was kind of nice. So, make sure I've got my windows open. So that's what's on the agenda for today. We're starting in on chapter 8, so that should be fun. Which is on torque, which rhymes with fork. Where is my participant list? There it is. Okay. Yeah, it's important. I realize this election is a little, scary and stuff, and can be consuming. But you do have to take care of your physical health and try to get outdoors and stuff. You can take care of your mental health as well. And so listen, I just want to start with some very sad news. I'm a bit shaken this morning, to tell you the truth. So this is about a student of mine in Physics 151, which is the course for physics specialists. So I'm the practicals coordinator for that course, and a student passed away on the weekend. His name was PHY131H1F. It's a picture of him from his LinkedIn profile. He was living at New College, apparently died off campus. So I'm working with the TAs and the other students in that course, but I don't know if you knew him, but I just wanted to say that he will be missed, and I do hope that we all can think about this, think about taking care of ourselves, our mental health, each other, and trying to work through this, because this is a bad tragedy. So sorry for the sad news, but I wanted to acknowledge Keshav. Okay, so last night on the Crowdmark, there was this chapter 7 pre-quiz. So I am the only one who's going to be marking this one. I haven't hired TAs to do that because I'm completely out of TA budget. I've actually blasted through my TA budget for marking, and I'm in a bit of trouble for that. But I'm going to go look through it. I've been looking through it, and so far it looks pretty good, and it seems to be a lot less glitchy. Maybe we're just getting used to this, but I would say I'm seeing a lot of fantastic work from you. So I'm going to go through there. It'll probably take me a couple of days, but basically I'm just looking to see if I can read it. So the 16 points is going to be a legibility thing. I mean, I might look, if it doesn't look like you followed the 4-step method, I might take off some marks or something like that. But basically, if you get 16 points, it means that things weren't too blurry or dark, and I thought I could read it. So hopefully that's clear. Why don't we just someone just asked, Dhruva, if I could do a YouTube video. Why don't we just do it right now? It's actually, this was pretty straightforward. So this will be your YouTube video. The 75 kilogram crate, basic idea is, you can sketch it if you want. So there's this ramp. There's the 35 degrees. This, I think, was the 12 meters, was the length of the ramp itself. So there's like the final position, and there's the initial position. And what was weird about this one is that it said constant speed. So to me, that means kinetic is constant. So we'll have to think about what that means in a minute. But I will define here the system is the crate plus the earth, because I'm going to use gravitational potential energy, plus the surface, because there's going to be this internal thermal energy. So 12 meters is that distance. This distance will be h, the amount of height that it fell. Okay, and we're trying to find delta U internal equals question mark. Okay. So basically, I'm going to assume here that energy becomes delta U internal. okay? And there's no external work done on the system. So if we look at K initial plus UG initial plus work equals K final plus UG final plus the delta U internal, then I think there will be some initial kinetic energy is moving, constant speed, plus there's definitely some initial MGH, gravitational potential energy, zero work, and then the final kinetic energy is the same, doesn't change. Plus then the UG goes away because it gets to the bottom. I'm going to set y equals 0 down there at base. And then, so it all gets converted to this delta U internal. So when you represent that mathematically, I'm just going to call it Ki. Let's actually say that Ki equals Kf equals K0 is constant to make this a bit easier. So I've got K0 plus mgh plus 0 equals K0 plus 0 plus delta U internal. So right away there, I can say that you can subtract the kinetic energy from both sides since it's constant speed. And then you've got mgh equals delta U internal. So we just need the h. And I think that if you look at sine of 35 degrees, it's going to be equal to opposite over the hypotenuse, 12 meters. So the h here is equal to 12 times sine of 35. So delta U internal is equal to the mass, 75 kilograms, times g, 9.8, times 12, times sine of 35. And so what did I get? I typed that all into my calculator. I got 5,100, and joules is going to be the answer because I've got SI units. So I was careful to keep everything in SI units. So the SI unit of energy is joules. Energy, okay. This is positive. Okay, so so basically the UG was converted to thermal by the friction. So that's all you need to do there, I think. 5.1 kilojoules, that could also work. Faison, how's it going?
Oh, no, I was going to ask you if we could go over the questions, and I just forgot to put on my hand. Thank you.
Sarah?
Hi, I had a question about the format in simplify and diagram. Do we always have to draw the diagram? Because when I was reviewing the notes for previous lectures, I noticed that for a lot of the chapter 7 problems, you did not draw the diagram. So for midterm 4, we would have to draw the diagram.
Yeah, so the answer is that, yeah, I'm going to instruct the markers for midterm assessment 4, which is the one coming up on November 17th. You have to draw the energy bar diagram. It doesn't have to be beautiful, but you have to draw the little bar things. Okay. It's worth 1 point or something.
Okay, thank you.
Okay. Yeah, sure. Osaze?
Hello.
Hi.
Hi, yes. I have a question about this. I actually got the same answer, but I did it slightly differently. Mm-hmm. So what I kind of used like chapter 4, because since it's sliding and, well, you mentioned friction in this, what I did, I found the coefficient of kinetic friction and then just multiplied it by the 12.
Yeah. Yeah, that works. So definitely, if you get the right answer and you've done correct steps, there's a lot of different ways to do it. I think this is the simplest way to do it. You don't have to find any forces or something like that, but as long as you were clear and went through some steps that were correct, then that should be fine. This way isn't as fun. True. But I mean, you weren't asked for the coefficient of kinetic friction. You weren't asked for what the force of friction was. So since you're not asked for it, just find how many joules were converted, and that's it. Just seems a little, try to do the simplest thing, right? So here's and again, this one's also pretty simple. 55 kilogram skateboarder wants to just make it to the upper edge of a half pipe, so that I can kind of try to draw that here like this. You've got starting down here, initial. He starts at a distance of 3 meters below, so this is final. So I think I'm going to call this H. H equals 3.0 meters. Okay. And then you've got some initial, V initial. So the question is to find V initial minimum. So this will be when V final equals 0, right? And so I'm going to define system is the skateboarder plus the Earth, because I'm going to use the gravitational potential energy. So that's why you have to include Earth if you're going to use MGH. So, and I can say something like, I guess, assume no air resistance. It's always a good one. Or friction. It says that there's, I guess you have to assume no friction. So no external work or loss to internal energy. So I'm running out of room for this diagram, but basically it's going to be K initial plus UG initial plus the work is equal to K final plus UG final plus the delta U internal. So I'm just going to draw, the K initial was big, and it starts at 0 plus 0. And then the K final is 0, so it all gets converted to that plus 0. So it's, let's just write it out here. 1/2 times M times V initial squared plus 0 equals 0 plus MGH plus 0. And then I'm going to divide both sides by the mass. Turns out the mass of the skateboarder doesn't matter. And I've got VI squared is equal to 2 times G times H. So VI is equal to the square root of 2GH. So it's equal to the square root of 2 times 9.8 times 3. Plugging that into my calculator, I got 7.7 meters per second. This is about 28 kilometers per hour, which is a reasonable skateboarder speed, I guess. So it's not like 28,000 kilometers per hour or something like that. It seems okay. So Dima asked a good question. For the first question about the crate going down, can we assume that the crate started and ended at rest? That's a great question. I don't really think you can, because it says constant speed, right? So for it to start and end at rest, you would get the right numerical answer, but I do think that's kind of wrong somehow. I mean, the point is, it doesn't matter what the speed was, because I just subtracted the kinetic energy off both sides. But I think it's kind of important to know that it's sliding at constant speed. If it starts at 0, then it has to accelerate up, right? And if it stops at 0, it has to accelerate down for some reason. So sort of maybe it's a philosophical question. Nicola, did you have a question?
Yeah. Hi. I was gonna ask for the previous question. I was gonna ask, could you also do it using calculating directly for the friction force using like all force diagrams? Would that be worth equal like points and everything?
Yeah. Yes. I think it's a little more work, but you still get 8 out of 8. Yeah.
Okay. All right. Thank you.
Okay. Like I say, there's more than one way to do that. I'm just showing you kind of the easier way. Hamad, how's it going?
Hi, Professor. I got 2 questions. So,
Sure.
you know how for question 2, you said that the answer was sort of reasonable, you sort of justified it, right, in solving and evaluate. But in question 1, you didn't say anything like that, like the energy is sort of reasonable. So do you have to compare it to something? Or like,
You don't have to compare it to something. I think with speeds, you can kind of think about maybe highway speeds or something, right? But with joules, I don't know what 5,000 joules is, and I don't expect you to. It's, I guess it's a lot, but if you had to pay for it at Toronto Hydro, it would be like less than 1 cent, right? So I don't know. I don't think, but so what I said here is that it's positive, which I guess is good. It has units of joules. That's about all you can say. Sometimes there's not much you can say in the evaluate stuff.
And for my second question, in the simplifying diagram, when you assume that there's no external work done, do you still need to mention work in part of the bar graph, or could you just leave it out?
I guess you could just leave it out. Yeah, if you just draw the bar graph. Normally I draw all three on the left and all three on the right, and just leave them to be 0. But I think you definitely want to include the kinetic and potential, right, on both sides, especially of this one, because that's what's happening, is that it's sloshing from one to the other.
Yeah. All right. Thank you so much.
Okay, sure. These energy bar diagrams, they're a little bit annoying to draw, I find, but they kind of, once you get used to them, they give you sort of a visual way of understanding where you're going with this problem, and so that it's not just a bunch of math. And I do think it is important. I think a lot of people just want to write down 1/2 mv squared equals mgh, and you're not really thinking about what happened there. You're comparing an initial when there was something was 0 to a final when the other thing was 0, and so it's you're conserving energy there. Let's move along. My lab and mastering. So just this morning, I posted a homework 8, which is due on Monday, November the 16th. That is actually 2 weeks from yesterday. It's after reading week. Also, I have posted an optional item called videos and practice for chapter. It's all optional, but this one's just not for homework credit. I should say not for homework credit item. Just videos and practice. Just to watch the videos. And these videos have this guy who, I don't know what his name is, but I call him just Buzzcut Guy. And he walks the plank in one of these videos, and it's fun to watch him do that because he gets a little scared. I'm not going to do that one. But I guess, hopefully he doesn't fall because he's computed the torque of this mass on the plank compared to his torque and going down. Okay. So the big idea, what's the big idea? You've got, so far, up until chapter 7, really, we've been assuming that objects are point particles. In chapters 8 and chapter 9, we're going to start thinking about extended bodies, which means that objects are not just points, but they have some shape and size. And where you apply the force on something will have an effect. So there's still force and energy and momentum, but there's some new things here, like torque, for example. And I brought with me a torque wrench, which just sort of shows, as you're turning it, it actually will show the foot-pounds. So it's force is measured in pounds, is an old unit of that, and foot is a measure of length. So force times length will give you the amount of torque that you're twisting on a wrench or on a bolt or something. So people use it for spark plugs because you're supposed to tighten them to a certain torque. So torque is kind of a big thing that's coming up in chapter 8. Chapter 9 will be a lot about rotation. Chapter 9 actually doesn't come up until the midterm 5, but we will be getting there. So we call a rigid body as a model for an extended object. We assume that the object has size, but the distances between all the points on the object remain the same. So the size and shape of the object itself doesn't change as you maybe rotate it or something, like these people holding onto each other. A rigid body possesses a special point such that if a force is exerted at that point, the object will not turn. So if you read through your book carefully, she goes through talking a lot about pushing an object with a pencil. So you're viewing this heart from above, and you are pushing it with a pencil in various different directions. Now, if you push it in a direction or at a place such that the force line passes through the center of mass, then it doesn't rotate as you push it because the torque is 0. If you push it you know, sort of not at a line that doesn't pass through the center, if like if you were to push it here, then it would turn as you pushed it. It would actually turn counterclockwise if you pushed it here. If you pushed it here, it would turn clockwise as you pushed it. So this is one way of thinking about the center of mass, is where when you push it, it doesn't rotate. Okay, so when you have a rigid body, you can sometimes make it rotate. A door is a good example of this. So when an object always turns around a particular axis, we call that rotational motion, and we call this axis of rotation the line that it rotates around. A good example of this is the hinge of a door. The hinge of a door is called the axis of rotation. And it turns out that if you're going to apply a force to the door, look at these three forces, for example, F1, F2, and F3. F1 and F2, F1 and F3 don't rotate the door. If you just push a door on its hinge, it doesn't rotate. If you push a door towards its hinge, then it also doesn't rotate. If you're going to actually open the door or close the door, you have to push or pull in a perpendicular direction that's not right on the hinge. So there's three factors that affect the turning ability of the force. One, the place where the force is exerted. Two, the amount of force. And three, the direction at which the force is exerted. So quick example here, F1 and F2, if they're the same magnitude, one is exerted on the hinge, one is exerted on the doorknob, and they do different things. They have a different torque on the door. And here the F2 has more torque. It's more able to rotate it. And then if you compare F2 to F3, those are applied at almost the same place, but they're applied at a different angle. And so a different direction. And they will also have a different torque because the F3 doesn't rotate the door. Let's see if this is making sense to you guys. Here are 4 different forces. Which of them will be most effective at opening the door? Find my holes here. Doing very well for time, so that's good. Okay. Let's see what people are voting here. Going once, I'll give you 5 seconds to click in. Okay. And it was 92% in favor of force F1, which I like. 8% were thinking F3. I think what actually happens is that with F3 will open the door, but with not as much torque. And so it's going to turn out that the torque has to do with this distance. I'm going to call it X at some point of the lever arm. So the lever arm for this is for force 3 is less than the lever arm for force 1. And that's why. So this direction is better. And then I can put this next slide on. But let's actually go to some of the hands that are up. I see Lauren, you put your hand up. How's it going?
Hi, I'm good. Actually, I just had a question about the practice midterm questions.
Yes. Yep.
You rounded to like 2 significant digits, but I thought because we use gravity as 3, it should be rounded to 3, and I got confused.
Did I mess that up? Could be that I'm wrong. It's the lowest number, right?
Yeah.
But yeah, and you're supposed to use 9.80. So this one I think is okay because 75 kilograms and 12 and 35, those are 2. You mean the second one? Yeah, again. So 55 and 3, I had to use 3.0 in this one, right? And that's 2 significant figures. So I should round to 2, I think.
Okay, I just thought if we used gravity, it would like add that to like the significant digits, but I guess I'm wrong.
You always use the lowest. So you're right, G is 9.80, but you use the lowest, the input number with the lowest number of significant digits is what determines it.
Oh, okay, right,
Okay.
okay.
Sure.
Thanks.
You're welcome. Nanako?
Hi.
Hi.
So I also have the question on the pre-quiz.
Yeah.
So like on the first example, you didn't write anything about no air resistance.
Yeah.
But like, are you supposed to write that or no?
No, I had a lot of, just something, just in the simplify and diagram step, you're supposed to write any assumptions that you might need. So I mean, there's no external work done as one of the assumptions. It's not a really strict rule.
Okay, yeah. Yeah, it's sometimes a little confusing on like what to write and what not to write.
Yeah, you could write
Yeah.
no, assume no resistance, I guess. But I mean, yeah, I think it might actually be a good idea to write that because you're assuming that the surface is where all the internal thermal energy is going. So I just missed it.
And another question. So when you're defining system, like on the second example, you wrote the skateboard and the earth, right?
Yeah.
Yeah, are you supposed to write the pathway that it takes, or like is that also a system or like not? Like I'm confused on like how to define a system.
Yeah, because the ramp could be one of them, right? As part of the system. So I would not. I do not include the ramp in this one. I guess I kind of could, but the point is that the ramp is not changing its energy in any way. When I say including the Earth, what I mean there is I'm using MGH. So MGH is actually a short form for this negative GMM over R, right? It's the gravitational potential energy of the system of the Earth and the object.
Oh, okay, I see.
Talking about an interactive force. So that's why I put plus Earth, but I don't put plus the only way I put the ramp on there is if there's friction being lost to the ramp and they need to use the surface there.
Oh, because there will be energy going on between
sucked into the ramp itself.
skateboard and the ramp if there is friction. Oh, okay, thank you so much. Yeah.
Those are excellent questions. It's good to hear from you. Let's move along a little bit. I wanted to talk about this torque equation. Okay, so this is from your textbook. The torque produced by a force. The torque produced by a force exerted on a rigid body about a chosen axis of rotation is plus or minus F times L times sine theta. So F is the magnitude of the force. L is the magnitude of the distance between the point where the force is exerted on the object and the axis of rotation. So I'm going to try to kind of draw that here. If I've got some object here, which can rotate around this axis, okay, and I apply a force, maybe here, F, okay, then what you would have is this distance from here to where I apply the force is called L. Okay, and then if you look at this is L and that this is force, then this angle here, theta, between the force vector and the vector which goes from the axis of rotation out to where you apply the force, that's your theta. Okay. And L has units of meters, force has units of newtons. So the SI unit for of torque, sorry for that typo, is the Newton meter. SI unit for force is Newton, SI unit for this L is meter, so it's Newtons times meters. Sorry about that typo. And torque, yeah, someone just asked, Annie asked a really good question. Torque, is torque a scalar? So it's a great question. Torque this is the magnitude of the torque. I don't think in this course we're going to get into the vector sign of it. So short answer is that torque is actually a vector in physics, but here this is we treat torque as a scalar here. Okay, so plus and minus determine clockwise or counterclockwise. So it has direction. Anyway, because it could be clockwise or counterclockwise. So maybe it's a vector. But in this equation, we treat it like a scalar. Domenico, is the Newton meter also a joule? Oh yeah, force times distance. The work equation, yeah, this is weird. So the work equation, that's a really good point, is that work is force times distance in the same direction. That's a joule. This is not a joule. This is Newton times meters, and they're in perpendicular directions. I think that's a coincidence. The unit of torque is not the joule, but I guess it's mathematically equal to it. Okay. And we're going to do the lever arm. Yeah, so, okay. Let's do this. So, example, Lewis uses a wrench, 20 centimeter long wrench to turn a nut. So let's try to draw it here. Here's the wrench. And here is the nut, I guess, can turn. Okay. So we'll call this the nut. This is the wrench. Okay. And this is 20 centimeters from here to here. Okay. The wrench handle is tilted. Oops. You know what? I think I just drew that wrong. It says that the wrench handle is tilted 30 degrees above the horizontal. So I drew it below the horizontal. So let's try to start that again. Luckily, I have a good eraser on this thing. So let's draw it like this. The handle is, which is this part, is 30 degrees above the horizontal. And Lewis pulls down with a force of 100 newtons, okay? And this is the, here's the nut. Here's the, I'm gonna call it 0.20 meters from here to here. Is that better? So the unknown that we're trying to find is the torque. Okay. And this is the force of Lewis on the wrench. So the system here is the wrench plus the nut. And we're trying to find the torque that Lewis exerted on the system. So they're connected together, right? The wrench plus the nut. So this is assume rigid body, I guess. Something like that. Wrench plus nut are connected. That's the idea. And then we can draw the force diagram, which is like this. Here's the force of Lewis on the wrench. Okay, and this is the rotation axis. Axis of rotation. And I'm going to say that counterclockwise equals positive. Okay. So we're going to use this equation 8.1, which is that the torque is equal to plus or minus F times L times sine of theta. I'm going to choose plus, since a wrench turns counterclockwise. If it pulls down on it, it's going to make the whole thing turn counterclockwise, so that's good. And then I'm going to draw these vectors. If this is your L vector and this is your force vector, then this will be the theta that you want. And then really messing this up. Sorry, guys. I gotta draw this again because I think I had this wrench the wrong way. So this is the thing, right? This is force. And then this is the wrench. Here's your axis of rotation. So wrong. So this L will be, so I got that wrong. I was originally thinking that the wrench was down below the horizontal, but it's above the horizontal. So the force is still down, force, but the L is up like this. L. Okay. So this is your angle right here. Theta. And then if you look at this as being 30, and this is right angle there, then theta is equal to 30 plus 90, which equals 120 degrees. Okay, so torque is equal to your 100 newtons times your L, which is 0.2 meters, times the sine of 120. So now, since I did this wrong, let me see if I can do that on my calculator. 120, and let's press sine. So 0.866 times 0.2 times 100. It's weird. I got the same answer even though I used 60 last time. So, okay, I got plus 17 newtons times meters. Okay. And I'll just say here this is positive since the system turns counterclockwise if it moves. Okay, figured it out. I wanted to do a couple of polls. I see a whole bunch of hands up. Maybe Hyamin, do you want to?
Hello, Mr. Harlow.
Hey, how's it going?
Hello. So I want to talk about the torque.
Talk about the torque?
Yeah.
About...
Yeah, talk about the torque.
Yep.
So does a pivot point equal to the rotational axis?
Yeah, those are the exact same thing.
And just
Actually,
one more thing, the questions from pre-quiz 7.
Yes.
So like the first question asked about the thermal energy, right?
Yeah.
And just like for my chapter 7 quiz, I wrote for the equation like showing the change in energy. Instead of work and change in U interval, I used E thermal final and E thermal initial. Like, is that also correct?
Could be. I mean, what happens is that whenever you have a process where there's some friction, you're creating thermal energy during the process, right? So I always just put it only on the right-hand side of the equation, and I don't put it over. There's no initial. I guess there would be an initial thermal energy because it's not like an absolute zero or something like that. But what matters is that you've created some thermal energy that's changed from initial to final. Those are good questions. Let me talk a little bit more about the sign convention business for torque. So this is a historical sign convention, which you could define it either way. But what we do in physics is we say that if a torque tends to produce a counterclockwise rotation, this is positive torque. I think the examples here are all showing the gravity force. If I hold my pencil and let it kind of fall due to gravity, gravity applies a torque around the axis of rotation where you're holding your pencil. So if you hold your pencil towards the right from the eraser, that's a negative torque of gravity. I guess if you twist it, then you're applying actually a positive torque. And then if you hold it to the left, then gravity produces a counterclockwise positive torque, and then you have to twist it up with a negative torque to counterbalance gravity. Okay. So let's do a poll question here. So what we have is a ladder leaning against a wall. The question is, what is the sign of the torque of the normal force of the wall on the ladder? So I'm going to draw it in red here. Normal force of the wall on the ladder is this force. And the question is that A, a positive torque, or is that B, a negative torque? Or would you say C, the torque is 0? Or would you say D, it depends on where we choose the rotation axis to be? It's really fun watching I can see the graphs growing and shrinking because people are thinking about it more, they're changing their answer. And just as a little warning, this is a trick question. Think about this one. Okay, 5 seconds to click in, please. 4, 3, 2, and 1. Always good to vote. So 35% of you noticed that you absolutely have to define, first you have to define where the rotation axis is. You cannot say anything about the torque until you know where the axis of rotation is. Okay, because it depends. I could put the axis of rotation right here, in which case it would be 0. I could put the axis of rotation down here at the bottom or somewhere in the middle, in which case it would be clockwise. So that would be a negative torque. So B is a good answer, but it's the correct answer is D. So let's do another one quickly here. So this says a ladder leans against the wall. Let's choose the rotation axis to be the bottom of the ladder. And now we can let's give you 20 seconds to click into this. Same question. Okay, I think I want to try to do this one. So just to show you how these things work. So this one's right. If this is the rotation axis, and this force will tend to produce clockwise. So it's negative, okay? Makes sense. Let's do a couple more of these. Oops. Oops. This one's negative because of this. Let me just go to the next slide here. Erase all the stuff I did. I think I was writing on the wrong slide. Okay, sorry. This is another question. There is a force of static friction of the floor on the ladder, and this is preventing it from slipping. So which way do you think is the sign of the torque of the static friction force of the floor on the ladder? I'll give you 30 seconds to think about this one. Sorry if I messed up that last poll. Okay. Let's end the polling. Share the results. This one is that the torque is 0. Okay. So hopefully this idea, so actually which way does it go is sort of a good question, but I think that the ladder might tend to slip to the right. So I think that static friction goes this way, not the other way, of the floor on the ladder. But anyways, if it's applied right at the rotation axis, then the torque is 0. Okay. And for this one, the torque is negative, okay, because it's clockwise. That's what I meant to write on this slide. And for this one, you have to define rotation axis. So there's something called gravitational torque. Where is the gravitational force exerted on a rigid body? Well, it's exerted to every single point, okay? But if you're calculating the torque due to gravity, you may treat the object as if all of its mass were concentrated at the center of mass. That's why the object's center of mass is sometimes called the center of gravity. So you can, to work out torques, you can imagine that the Earth comes up and grabs with a little hook right at the center of mass and pulls at that point. So I'm going to skip that one. This is this lever arm idea, which is that if you've got a force that's acting on an object, so here's an axis of rotation and here's a force, here's your vector L from the axis of rotation to where you apply the force. Then by geometry, there's a distance, x, which is the distance between the force line and perpendicular distance from the force line to the axis of rotation. And that's going to be L sine theta. So you can rewrite torque as being the force times this distance. And I call it this lever arm X. I call it the lever arm. It's the distance between wherever your force line is and the object, right, and the rotation axis, sorry. Once again, I'm kind of running out of time here. Let's do one more of these polls, and then we'll call this quits. A uniform ladder leans against the wall. You choose the rotation axis to be at the bottom of the ladder. What is the sign of the torque of the force of gravity on the ladder? Remember, clockwise is defined to be negative, and counterclockwise is defined to be positive. Let's give you another 5 seconds to click in and answer. Okay, and 69% of you were saying that it should be a positive torque, and I think that's correct. So if this is the axis of rotation down here, and this is where the force of gravity is applied, it goes up and hooks at the center of mass. It's a uniform ladder. It's going to tend to rotate it counterclockwise. Okay, so that's when I define that as positive. So let me, oops. This. I will do an example of this actual ladder, but I'm going to do that on Friday, I think. So run out of time a little bit. I do would like you to continue reading chapter 8, section 8.3 in static equilibrium, 8.4 center of mass, and that's where we'll end it from before reading week here. So plan to meet up with your practical pod mates during Friday's class in the Microsoft Teams. There's going to be a team up quiz based on some of this chapter 8 stuff that we've been talking about. There'll be 3 questions worth 5 points each, so it's a 15-point quiz that you can do during 10 minutes during Friday's class. If you can't attend or something, or if you're watching this in the YouTube, then you can do it over the weekend, but it's definitely good to try to meet up with friends in the class to do these ones. So I'm going to turn off the recording and then I go to all the hands that are up here. So.